Hello, Namaskar everyone. Myself, Dr. Baby Bhattacharya, Associate Professor and Head of the Department of Mathematics. Today, I'd like to deliver a lecture in Engineering Mathematics, which one is a common syllabus for all the engineering students of NIT Agartala. Here is my presentation. I am to start with the chapter of Laplace transform, and our objective is to know the basic of Laplace transform with some properties. Actually, here we are all the engineering students, and our main focus is to find the solution of physical problem, and every physical problem converges to find the solution of an equation. The equation, it may be algebraic, it may be a differential equation or a partial differential equation. So why we are here to study Laplace transformation? What is that Laplace transformation? The Laplace transformation is an important operational method for solving linear differential equation. It is particularly useful in solving initial value problems connected with linear differential equations, ordinary as well as partial. The advantage of Laplace transformation in solving initial value problems lies in the fact that initial conditions are taken care of at the outset and the specific particular solution required is obtained without first obtaining the general solution of the linear differential equation. It is applicable to continuous function, piecewise continuous function, periodic function, step function, and impulse function. It has many important applications in mathematics, physics, optics, electrical engineering, control engineering, signal processing, and also probability theory. So, that is why we are to study this Laplace transformation. Now, how this transformation is coming? Actually, Laplace transformation, it is coming from the idea of integral transform, and this Laplace transformation is a particular integral transform. Now, what is integral transform? An improper integral of the form integration minus infinity to plus infinity kst ft dt is called the integral transform of the function ft if it is convergent. Now, improper integral here means whenever we are considering a definite integral, either it is of the form having the limits containing infinity, or it may so happen that the integrand, it is having the limits, finite limits, but it is not defined in between the limiting values. So such kind of integrals are improper integral. Here we are considering an improper integral which one is having limits from minus infinity to plus infinity and a function of kst ft dt. Whenever this integral is existing, it convergent, then it is known as the integral transform of the function ft. And that integral transform is usually denoted by f of capital F of s or transformation for, that is capital T of small ft. Thus, we denote this integral transform fs is equals to transformation of the function ft as the improper integral integration minus infinity to plus infinity kst ft dt. We are using here the relation number 1. Now, the function kst appearing in this integral, it is known as the kernel of this transformation, where s is a parameter and that one is independent of t, and that s may be real or complex. So we do have the idea of an integral transform with the utilization of this kernel. To give some example, we must name a few integral transforms here. For example, we are considering Henkel transform, we are considering Laplace transform, we consider Fourier transform and also Mellin transform. But in our syllabus, we do have only the Laplace transformation and its application. So we are focusing on that one. And to define a Laplace transformation of a function, uh, we consider a function ft which one is defined for all t greater than equals to 0, and the integration 0 to infinity e to the power minus st ft dt is existing, then it is a function of the parameter t. The function of s, that one we denote here by small f bar s, or sometimes we use here as capital Fs, and this is called the Laplace transformation of the given function ft over the range of values of s for which the integral is existing. The Laplace transformation of this function ft is also denoted by capital L of ft, or sometimes we denote this one simply by L of f. Therefore, the Laplace transformation of the given function ft is appearing in the form of a improper integral integration 0 to infinity e to the power minus st ft dt, which one is denoted by f of s. Now here we are simply from the definition of integral transform, we are using the kernel here as e to the power minus st, and we are considering the limit here from 0 to infinity. So we have the Laplace transformation of the function ft in the form of capital Fs, provided the integral is existing. The function ft is called the inverse Laplace transformation of the function capital Fs, and it is denoted by L inverse of Fs, where we are getting the original function ft. So L is the operator where we can find the Laplace transformation of the function by using the kernel e to the power minus st. Now, our main objective for this class is to find the Laplace transformation of some elementary function by using this definition, and we will prove how we can find the Laplace transformation of such simple functions. So, first we are considering the Laplace transformation of a function which one is a constant function, or rather we are considering a particular one that ft is equals to 1, where the function is defined for all t greater than equals to 0. Now we are applying here the definition of the Laplace transformation to find the same for this function ft whenever it is defined as 1. We consider the Laplace transformation of this function ft equals to 1 from the definition as integration 0 to infinity e to the power minus st ft dt, which one is equals to integration 0 to infinity e to the power minus st ft is replaced by 1 dt. Now after integrating we obtain that one is e to the power minus st whole divided by minus s. We put the limits from 0 to infinity. Now we observe that e to the power minus st is approaching to 0 whenever we are putting t is approaching to infinity, and s is strictly greater than 0. So accordingly we are getting the Laplace transformation of the function ft is equals to 1 is 1 by s, provided s is strictly greater than 0. That means the Laplace transformation of the function ft when ft is equals to 1, the Fs function, that is capital Fs, is appearing in the form of 1 by s, where s is strictly greater than 0. Now let us move for another function which one is in the form of exponential function, that is ft is given as e to the power minus at, where small t is greater than equals to 0, and we are considering a as a constant. So our objective is to find the Laplace transformation of this function ft, where ft is equals to e to the power minus at. Again we are applying here the definition of Laplace transformation, that is Laplace transformation of ft is equals to integration 0 to infinity e to the power minus st ft dt, that is equals to integration 0 to infinity e to the power minus st, ft is replaced by e to the power minus at, integration is with respect to t dt. So we do have integration 0 to infinity e to the power minus s plus a of t dt. And performing the integration, we have that one is minus of e to the power minus s plus a t whole divided by s plus a, limit is from 0 to infinity. If we put t is approaching to infinity, then we have e to the power minus s plus a t of t is approaching to 0 if s plus a is greater than 0. So, we could find the Laplace transformation of this function e to the power at is equals to 1 by s plus a, provided s is greater than a. So, for this second function, whenever we are concerned to find the Laplace transformation of this exponential function e to the power minus at, we do have the Laplace transformation of this function is coming 1 by s plus a, provided s is strictly greater than minus a. Now, we can find the Laplace transformation of this exponential function whenever it is given in the form of e to the power plus at. Simply changing a to minus a in the previous function, we can find the Laplace transformation of this function e to the power at, and that will be coming, see, for e to the power minus at, the Laplace transformation of the function, it was 1 by s plus a. If we replace a by minus a, so accordingly Laplace transformation of the function e to the power plus at, that would be 1 upon s minus a. So we have the Laplace transformation of the function e to the power at as well as e to the power minus at. Our next target is to find the Laplace transformation of circular function. First, we are considering the function ft as sin at. It is defined for all t greater than equals to 0 and a is a constant. So, to find the Laplace transformation of this function ft, we are applying here the definition, and accordingly we are getting that Laplace transformation of sin at is equals to integration 0 to infinity e to the power minus st sin at dt. So here is a function, the integrand is of the form exponential function multiplied by circular function, that is you can consider here as e to the power ax sin bx form. So applying the formula, we are getting that the integration is giving us that e to the power minus st whole divided by s square plus a square into minus s sin at minus a cos at, limit it is from 0 to infinity. Now, we are considering minus s upon s square plus a square and the limiting value of e to the power minus st sin at whenever t is approaching to infinity, minus a upon s square plus a square limiting value of e to the power minus st of cos at whenever t is approaching to infinity, minus for the lower limit 0, it would appear as a upon s square plus a square, and that is true for s greater than 0. And both the functions e to the power minus st sin at as well as e to the power minus st cos at, both are tending to 0 whenever t is approaching to infinity. Eventually, we are getting that Laplace transformation of the function sin at is equals to a upon a square plus a square whenever s is greater than 0. So, for this first circular function, we do have the Laplace transformation of sin at is equals to a upon a square plus a square whenever s is strictly greater than 0. Now, we can go for the Laplace transformation of other circular functions like cos at and also some other functions. Before that, we would like to verify the result by considering an other approach where we are using the relation sin at is expressible in the form of exponential function e to the power I at minus e to the power minus I at whole divided by 2i. as we know how to find the Laplace transformation of the exponential function. So it is easier one for us to find the Laplace transformation of this circular function sine 80 in terms of the exponential function. So that is appearing that Laplace transformation of sine 80 is nothing but Laplace transformation of e to the power I80 minus e to the power minus I80 whole divided by twice I. Now from two part we do have the Laplace transformation. It is coming in the form of 1 by 2i whole of 1 by s minus ia minus 1 upon s plus ia. And after simplification, we do have the result is appearing as a upon s square plus a square. It means in this approach also we are having the same the result is same for the Laplace transformation of the function sine a t by considering the form of this circular function in the form of exponential function. So to move forward, we do have the Laplace transformation of the elementary function, which one is again a circular function cos a t defined for all t greater than equals to 0, a is constant, by using the formula that Laplace transformation of cos a t is equals to integration 0 to infinity e to the power minus st cos a t dt. Applying the formula of exponential function with that cos a t, we do have that one is e to the power minus st whole divided by s square plus a square of minus s cos a t plus a sin a t. The limit is from 0 to infinity, and that appears of the form s upon s square plus a square, provided s is strictly greater than 0. Now we can verify the same result by applying the above relation of relation for cos a t, that is cos a t is equals to e to the power I a t plus e to the power minus I a t whole divided by 2. So we can verify the result, and accordingly we will be getting that Laplace transformation of cos a t is equals to s upon s square plus a square. Now we can find the Laplace transformation of other functions also. Say the first function, it was Laplace transformation of ft whenever ft is equals to 1. Now what will be the result whenever we are considering the ft function is coming in the form of t or t square or in general t to the power n. So that also we are considering, and the function we are considering in general as ft is equals to t to the power n for all t greater than equals to 0, and n is a positive integer. Now we have to find the Laplace transformation of t to the power n. We apply the definition here. We do have Laplace transformation of t to the power n is equals to integration 0 to infinity e to the power minus st t to the power n dt. Now what we do, we integrate partially, that is by integration by parts. We do have Laplace transformation of t to the power n is equals to minus t to the power n e to the power minus st whole divided by s, putting the limits from 0 to infinity, minus the remaining part is integration 0 to infinity minus 1 by s whole into e to the power minus st n into t to the power n minus 1 dt. Now if s is greater than 0, we apply the L'Hospital rule here successively, and we can show that Laplace transformation of t to the power n is appearing in the form of n by s, and the remaining part is Laplace transformation of t to the power n minus 1, because in the second part we do have it is e to the power minus st t to the power n minus 1 dt if we consider the variable with respect to t, and the remaining part it is 1 by n in n by s. So accordingly we are getting that the Laplace transformation of t to the power n is equals to n by s into Laplace transformation of t to the power n minus 1. That is, continuing this one, we do have n in n by s into n minus 1 by s Laplace transformation of the function t to the power n minus 2 for s greater than 0, as t is approaching to infinity. So, after applying this L'Hospital rule, we are now in a stage the Laplace transformation of t to the power n is equals to n by s into n minus 1 by s, and remaining the Laplace transformation of t to the power n minus 2. We repeat this step, and finally we have Laplace transformation of t to the power n as n upon s into n minus 1 by s into n minus 2 by s dot 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 up to 2 by s into 1 by s, and Laplace transformation of t, which one is coming in the form of 1 by s. So after simplification we do have that Laplace transformation of t to the power n is n into n minus 1 into n minus 2, this up to 2 into 1 whole divided by s to the power n into s, that is n factorial by s to the power n plus 1. So we have the Laplace transformation of the function ft whenever it is given in the form of t to the power n, and n is an integer, so we have the result in the form of n factorial by s to the power n plus 1. So this is the Laplace transformation of t to the power n, and we can prove the same result by another approach also, and the alternative approach is coming from an improper function which one is known as a gamma function. What we do there? We consider the substitution of st by a variable x. Accordingly, we obtain t is equals to x by s and dt is equals to dx by s. So the Laplace transformation of t to the power n, it is appearing from the definition as integration 0 to infinity e to the power minus x, and the function it is x by s whole to the power n dx by s, that is coming 1 by s to the power n plus 1 integration 0 to infinity e to the power minus x to the power n dx. Now we put this one as n factorial by s to the power n. How? You see, we are considering here the improper integral, integration 0 to infinity e to the power minus x to the power n dx. So we are considering here the gamma function, and we note that the gamma function is defined as gamma n. What is gamma n? Integration 0 to infinity e to the power minus x to the power n minus 1 dx. When this integration is convergent existing, then we have this is the gamma n function, and gamma function n is equals to n minus 1 factorial whenever n is an integer. So gamma n is equals to n minus 1 factorial, and if we replace n by n plus 1, accordingly we are getting gamma n plus 1 is equals to integration 0 to infinity e to the power minus x to the power n dx. So that one is equals to n factorial, and using this result we have the Laplace transformation of t to the power n is equals to n factorial by s to the power n plus 1. So by considering both the approaches, we are getting that yes, the Laplace transformation of t to the power n is equals to n factorial by s to the power n plus 1. Now if some particular cases are arising to find the Laplace transformation of t or the Laplace transformation of t square or t cube, accordingly we can find all the values of Laplace transformation of t square by using this formula, and it is valid for all integral value of n. So this is the Laplace transformation in respect of this function t to the power n. Now we are to study some properties. Actually, to consider the elementary functions, we have the constant function, we have the exponential function, the circular functions, and also the algebraic function in the form of t to the power n. Now we are focusing on some property of Laplace transformation, and first we are considering the linearity property of Laplace transformation. Here we are considering two functions ft and dt, and for which the Laplace transformation is existing. we are not concerned when the Laplace transformation is existing, that will appear later on. So if we are considering ft and gt for which Laplace transformations are existing, then Laplace transformation of ft plus gt is nothing but summation of Laplace transformation of ft and gt. We can prove this one by simply applying the definition. So we are considering Laplace transformation of ft plus gt, and according to the definition it is integration 0 to infinity e to the power minus st, and the function it is ft plus gt, integration is with respect to t, so that one is dt, is appearing integration 0 to infinity e to the power minus st ft dt plus integration 0 to infinity e to the power minus st gt dt. It means we do have that Laplace transformation of ft plus Laplace transformation of gt. Now, whenever we multiply the function ft by a constant k, that is k of ft, what is the Laplace transformation of that function? That Laplace transformation of that function is nothing but in terms of the definition, Laplace transformation of k into ft is equals to integration 0 to infinity e to the power minus st k times ft dt. So k is out of this integration as constant, integration 0 to infinity e to the power minus st ft dt. It is coming that k times of Laplace transformation of the function ft. So in view of this two property, that is Laplace transformation of ft plus gt and that of Laplace transformation of k times of ft, we have the conclusion that this Laplace transform operator L, it is a linear operator. Now we can generalize this conclusion, this result in terms of a more generalized form. From the above ideas, we do have that Laplace transformation of a of ft plus b of gt is nothing but a times Laplace transformation of ft and plus b times Laplace transformation of gt for any two constants a and b. Now we are generalizing this result and we obtain that Laplace transformation of summation over I from 1 to n ai fi of t is equals to summation over I from 1 to n ai Laplace transformation of the function fit, and it is true for all the constants a1, a2, a3 up to an. So the linearity property we can generalize in this way. Now we'll focus to find the Laplace transformation of the hyperbolic function. According to the definition of hyperbolic function, we have sine hyperbolic at is equals to e to the power at minus e to the power minus at by 2. So our objective is to find the Laplace transformation of this hyperbolic function, that is Laplace transformation of sine hyperbolic at. We will show that the transformation of this function is a upon s square minus a square whenever s is strictly greater than mod a. Now to find this result, we have to apply the definition of Laplace transformation, as well as we have to apply the relation of sine hyperbolic function in terms of exponential function, that is sine hyperbolic at is equals to e to the power at minus e to the power minus at by 2. So eventually we have that Laplace transformation of half of e to the power at minus e to the power minus at. As we know how to find the Laplace transformation of this exponential function e to the power at as well as e to the power minus at. So we do have the result is as half of 1 upon s minus a minus 1 upon s plus a. There is a mistake. It would be 1 upon s plus a. So after simplification, we do have that one is a upon s square minus a square for all s greater than mod a. Now, using the same technique, we can find the Laplace transformation of the hyperbolic function in the form of cos hyperbolic at, and that will be that Laplace transformation of cos hyperbolic at is equals to s upon s square minus a square for all s strictly greater than mod a. So this is the result. These are the results for hyperbolic function, and to find the Laplace transformation of both cos hyperbolic function as well as uh, sine hyperbolic function. Now, if anybody raised the question, would it be possible to find the Laplace transformation of sine at and cos at from the relation of uh, exponential function, that is e to the power I at is equals to cos at plus I sine at? If we find the Laplace transformation of this function, then we can verify that yes, the Laplace transformation of sine at is equals to a upon s square plus a square, and that of cos at is equals to s upon s square plus a square. So it is very easy one. Only we have to apply here the relation as e to the power I at is equals to cos at plus I sine at. Now what we are doing, we are writing the Laplace transformation for both the side. As we are to find the Laplace transformation of cos at and sine at in the left hand side, what we are considering, we are applying here the linearity property for cos at plus sine at. So that is coming as Laplace transformation of cos at plus I times Laplace transformation of sine at. In the right hand side, we do have Laplace transformation of e to the power I at. We know the exponent for this exponential function, Laplace transformation is coming 1 by s minus I a. Now, the right hand side, if we go to multiply both the sides by s plus I a, accordingly we are getting that one is s plus I a by s square plus a square. Now, if we compare the real part as well as the imaginary part from both the sides, and accordingly we will be getting that Laplace transformation of cos at is equals to s upon s square plus a square, and that of sine at is equals to a upon s square plus a square. So by this approach also we are getting the same result for the Laplace transformation of both the circular functions cos at as well as sine at, as we have previously from the definition of the function. Now we are to find the Laplace transformation of some easy problems. First one is to find the Laplace transformation of 5t cube plus 3t square minus 6t plus 3 times e to the power minus 5t. Simply by applying the formula that Laplace transformation of t to the power n is equals to n factorial by s to the power n plus 1, we can find the Laplace transformation of the first part, and that one is 5 times into 3 factorial by s to the power 3 plus 1. So it is coming 30 by s to the power 4. Plus, for the second part, we do have 3 times Laplace transformation of t square, that is 3 into 2 factorial by s to the power 2 plus 1. So automatically we are getting that one is 6 by s cube minus 6 times Laplace transformation of t. So it is 1 by s square plus 3 times Laplace transformation of e to the power at form. So it will be s plus a form, that is 3 by s plus 5. So for the first problem, we do have the result is 30 divided by s to the power 4 plus 6 divided by s cube minus 6 divided by s square plus 3 divided by s plus 5. Now, if we are to find the Laplace transformation of the function cos square 3t plus sine 5t sine 2t, we have only the formula to find the Laplace transformation of circular function in the form of cos at. But here is the case to find the Laplace transformation of cos square 3t. So we have to replace this cos square 3t by half of 1 plus cos 6t form, and accordingly we can find the Laplace transformation of 1 as well as Laplace transformation of cos 6t by the formula. In the remaining part we do have that the requirement is the Laplace transformation of sin 5t into sin 2t. So here we are applying here as a half of that cos 3t minus cos 7t. So the function is a simple one, and by the elementary function cos 80, that is cos 3t and cos 7t, we can find the Laplace transformation as s upon s square plus 3 square minus s upon s square plus 7 square. I think minus is missing here, so it would be half of s upon s square plus 3 square minus s upon s square plus 7 square. So by using all these formulae for elementary function, we can find the Laplace transformation, this one by using linearity property also. If we consider the problem number 3, the requirement is to find the Laplace transformation of a cubic function, that is cos cube 2t. Now, as we know the Laplace transformation of cos 80, so our first objective is to convert this cubic function into that one cos 80 form. So we are writing this as cos 60 is equals to 4 cos cube 2t minus 3 cos 2t, and replacing this one we do have cos cube 2t is equals to 1 by 4 whole into cos 60 plus 3 cos 2t. Now we can find the Laplace transformation in the right hand side. So accordingly we do have that one is 1 by 4 of s upon s square plus 6 square whole plus 3 times s upon s square plus 2 square. So we can find the Laplace transformation of this function also. Now we are to remember some important result to find the Laplace transformation whenever we are considering the power is beyond 3 or 4. That is, the circular function is appearing on the form cos to the power n theta or sin to the power n theta. Now, to remember these two formulae, we do have cos n theta is expressible in the form of 2 to the power 1 minus n whole into cos n theta plus nc1 cos n minus 2 theta plus nc2 cos n minus 2 theta plus dot dot. This is for cos to the power n theta. For sin to the power n theta, we do have this one as 2 to the power 1 minus n into minus 1 to the power 1 minus n whole divided by 2 of the function sin n theta minus nc1 sin n minus 2 theta plus sin n minus 2 theta minus, here is an alternating series plus minus. So we can remember these two formulae to evaluate the Laplace transformation of a function whenever it is given in the power of a circular function. To illustrate this formulae, we have one example, question number 4, as the requirement is to find the Laplace transformation of the function 64 times sin to the power 5t plus cos 2t plus 5. Now, here it is of the form sin n theta form, that is sin to the power 5t. So we can express sin to the power 5t by using the above formula as 1 by 2 to the power 4 of sin 5t minus 5c1 sin 3t plus 5c2 sin t. So that one is coming in the form of 1 by 16 of sin 5t minus 5 times sin 3t plus 10 times sin t. So we can find the Laplace transformation of this function, where we have to apply only the Laplace transformation of the function sin 80 form for all these three parts. Now, the remaining part we have, this one is as cosine function of 2t plus 5. Now, for this cos 2t plus 5 expanding, we do have cos 2t cos 5 minus sin 2t sin 5. So, one part is constant and another part is cos 2t, and the remaining it is sin 2t. So, accordingly, by applying the Laplace transformation of cos 80 and that of sin 80, we can find the Laplace transformation, and by summing these two parts we will get the ultimate result for this problem number 4. Okay, then we have to find the Laplace transformation of the function e to the power 2t of sine hyperbolic square at. Now only we know the Laplace transformation of the hyperbolic function sine at as well as cos at. So what we here consider is that whenever it is given to perform the Laplace transformation of hyperbolic function in the square form, we express this as sine hyperbolic at is equals to e to the power at minus e to the power minus at whole divided by 2 and its whole square. And see, this hyperbolic function is multiplied by e to the power 2t. So we write all these terms in terms of this exponential form, and accordingly we are getting the requirement is that we have to find the Laplace transformation of e to the power 2t whole multiplied by e to the power at minus e to the power minus at by 2 whole square. So that one is coming as 1 by 4 Laplace transformation of e to the power 2t whole multiplied by e to the power 280 plus e to the power minus 280 minus 2, and after simplification we have this result. So it is easy to verify that the result it is coming in this form. Now it may so happen that the function is defined in two or more than two intervals. Then also we can find the Laplace transformation by using the definition. For example, the function ft it is defined in the form of ft is equals to t by k whenever t is lying from 0 to k, and the function is defined as 1 for all t strictly greater than k. So by applying the definition of Laplace transformation, we can find the Laplace transformation of this function ft. What we do here is first we apply the definition of Laplace transformation is that Laplace transformation of ft is equals to integration 0 to infinity e to the power minus st ft dt. Now we break the limit first from 0 to k then k to infinity, and accordingly we obtain integration 0 to k e to the power minus st ft dt plus integration k to infinity e to the power minus st ft dt, and performing this definite integral and putting the limits will be getting the result for the function also. So it is easy to find the solution. And to give some other problems, I am noting here that from the first principle we can find the Laplace transformation of the function 1 plus cos 2t, and some other problems are there to find the Laplace transformation, such as the first problem is sin t multiplied by cos t, second one is sin 2t sin 3t, and in the third case we are considering a function as sin cube 2t. So one may consider this one as sin to the power n theta form, or by considering sin 60 also it is expressible. So anyone can go according to the comfortability, and in the easiest way they can find the Laplace transformation of this function. Next one is sin 2t cos 3t, that one is also easy, and the fifth one is cos at multiplied by sin hyperbolic at. So what we will consider here for the hyperbolic function will be applying here the definition of hyperbolic function, and cos at we have, so accordingly we can find the Laplace transformation by using the definition. Now the case is to find hyperbolic function in the form of, the sixth case is sin hyperbolic cube t. simply we'll put the definition of sine hyperbolic t function and whole to the power 3. By expanding that one, we'll find the Laplace transformation. So this we can find 7 and 8 also, but for 9 and 10, for the case 9, ft is given in 3 parts, t square whenever 0 less than t less than 2, and it is t minus 1 in the interval 2 to 3, and it is 7 for all t greater than 3. So from the definition, we are expressing this as integration 0 to infinity. So we will be breaking this one 0 to 2. The ft function will be coming as t square. From 2 to 3, it is appearing as t minus 1, and finally for all t greater than 0, greater than 3, it would be 7. So we can find the definite integral, and accordingly we will be getting the Laplace transformation of this function. And also the problem number 10. So we have discussed how to find the Laplace transformation of elementary functions, and whenever the function it is given in some intervals, sub intervals, then also we can find the Laplace transformation of the function. Now, one important aspect I must mention here is that if it is the case to find the Laplace transformation of the function ft whenever it is given that t to the power minus half, then how to find the Laplace transformation of this function? Actually, here we will be applying the gamma function, and we know that gamma half is equals to root pi. Using that value, we will be finding the Laplace transformation of t to the power minus half. So if we simply apply the formula for Laplace transformation of t to the power n, that one is coming as gamma n plus 1 by s to the power n plus 1. Now we are replacing that n by minus half. Accordingly, we are getting gamma of minus half plus 1 whole divided by s to the power minus half plus 1. So we are getting it is gamma half whole divided by s to the power half. And we are using here the result gamma half is equals to root pi. So the Laplace transformation of t to the power minus half, it is coming as pi by s whole to the power half. So different cases we can consider, and we can find the Laplace transformation of the function ft. Now one more property I'd like to discuss here, that one is known as the change of scale property. Say we are given the Laplace transformation of the function ft is equals to f bar s, then for any constant a we can find the Laplace transformation of the function f of at, and that one is 1 by a f bar of s by a. Moreover, if the Laplace transformation of ft is f bar s, we could find the Laplace transformation of the function f of t by a also, and that is a times f bar as. Now let us verify this both the results. By definition, we can find the Laplace transformation of the ft is integration 0 to infinity e to the power minus st ft dt, which one we are denoting by f bar s. So this is our relation 1. And by definition, Laplace transformation of f of at is equals to integration 0 to infinity e to the power minus st f of the function at dt, and we denote this one as f bar of as. Some typical error is there. So to find the relation between these two integral, we consider at as a new variable u, and accordingly we change dt by 1 by a du. Now changing the limits of the integral in the equation 2, we obtain that Laplace transformation of f of u is coming Laplace transformation of the function f of at, and that one is integration 0 to infinity e to the power minus s by a u f of u 1 by a du. We replace the dummy variable u by the original variable t, and accordingly we obtain that it is coming 1 by a integration 0 to infinity a to the power minus s by a t f of t dt. So this is the relation 3. Now if we compare the integrals in equation 1 and 3, we obtain that the integrals in 3 it is similar to that of in the relation 1 with the replacement that s by a it is appearing in place of s. That means the integral in 3 must be of the form f bar s by a. That is, we are writing the Laplace transformation of the function f of at is equals to 1 by a f bar s by a. Say this is the relation number 4. Now, to obtain the second part of this property, what we consider, we change a by 1 by a and you put in this relation 4. Accordingly, we obtain the Laplace transformation of the function f of t by a, and in the right hand side we are getting a times f bar a of s. We are putting this relation as 5. Now, both 4 and 5 are called the change of scale property. Whenever we are given the Laplace transformation of the function f of t, if it is the requirement to find the Laplace transformation of f of at as well as Laplace transformation of f of t by a, we can find the Laplace transformation by using these two results 4 and 5. So, um, to apply these two properties, we are to illustrate by easy examples, and if you consider example 1, we are given that Laplace transformation of ft is a logarithmic function s plus 3 by s plus 1, and then we have to find the Laplace transformation of the function f of 2t. So you see how our a is here 2, and by change of scale property we can find the Laplace transformation of the function f of 2t by 1 by 2 log of s by 2 plus 3 whole by s by 2 plus 1, and by simplifying this one we do have half of log s plus 6 by s plus 2. So this is coming from the property, that one is change of scale property. One more example we are citing here is that a function that is Laplace transformation of the function sine root t is given as under root pi divided by 2s into under root s whole into e to the power minus 1 by 4s. Now, the requirement is to find the Laplace transformation of the function sine 2 root t. So, our original function is sine root t. We have to replace this one in the form of sine at form, and that is why we are writing that sine 2 root t as sine under root 4t, and our requirement is to find the Laplace transformation of sine under root 4t. So a is here equals to 4, and by applying that change of scale property we can write this one as 1 by a into s is replaced by s by a. So accordingly we are getting the result, that one is 1 by 4 under root pi whole divided by 2 into s is replaced by s by 4 into under root s by 4 whole into e to the power minus 1 by 4 into as s is replaced by s by 4, and simplification is giving us under root pi divided by s into under root s whole into e to the power minus 1 by s. So we can apply here the change of scale property to find the Laplace transformation of such requirements. Other examples are also there to find the Laplace transformation by using the change of scale property. Here is error function is there, and some other functions are there. So we can conclude that if once we know the Laplace transformation of the elementary function, then we can apply this one to find the Laplace transformation of the function whenever it is appearing in the form of Laplace transformation of f of at, or it may so happen that it is appearing of the form of f of t by a. So this property is also applicable to find Laplace transformation of such kind of functions. Now, from this class we have come to know that by applying the definition, how to find the Laplace transformation of elementary functions and the properties including linearity property and change of scale property. And also we have come to know how to find the Laplace transformation of the same function sin 80 by considering different approaches. So we can apply all these results to find Laplace transformation of other functions also. So for this lecture we are having up to this much, but next our main focus will be to go for the uh, find the sufficient condition for the existence of Laplace transformation. Yet not we discussed when the Laplace transformation of a function will be existing. Only we have searched how to find the Laplace transformation of some function whenever it is defined. But to find the sufficient condition for any function for the existence of its Laplace transformation, that one is very important. So we'll be considering that issue in our second lecture, and also with the other application, as we have to apply this Laplace transformation to find the solution of equation, and the solution of equation, it may be for differential equation, ordinary differential equation, partial differential equation. So that will be applicable where it is required. And to prepare this lecture, I have studied the books, that is Laplace Transform by Shom series, Tata McGraw-Hill publisher, and also J.K. Goel and K.P. Gupta, and two others from Springer. And I hope we have come to know a brief about the Laplace transformation and why the Laplace transformation is required, and how to find the Laplace transformation of the simple functions. And next class we will be focusing on the sufficient condition for the existence of Laplace transformation and also other properties of Laplace transformation. So that's all from my side for today's lecture. Thank you all for being with me. Thank you very much. Namaskar.